Okay, everybody.
Slow down and speed up.
Okay, so let me say something about the next. So, so what I want to do is I'm going to talk a little bit about localizations today, but I'll probably restrict myself mostly to domains. So I'm giving you the problem set to kind of sort out a few of the details in the more general case. So I think all of you have seen localizations, at least in the setting of domains at some point or another. So this is the way that you sort of make fractions, even with zero divisors. If you have a commutative ring, perhaps for parts A and B without identity even, and S inside R, a multiplicatively closed subset. Usually the multiplicatively closed subset is assumed to not contain zero, but this all works out sort of anyway, if you allow zero rings sometimes.
So are we assuming no or yes?
No or yes for what?
Can we, when we say multiplicatively close, are we yes assuming that there's no zero?
No, you're not assuming that.
Okay.
Right, because all this, yeah, so let me think about it as I tell you, but, so we're gonna define this relationship, R, S is equivalent to, or is related to R prime, S prime, if and only if there's an S double prime and S, such that S double prime times its difference is zero. Notice that this thing is the old sort of cross product, where you compare two fractions, and this little, thing is what's needed, for doing, zero divisors. This is, you're going to burn me in effigy with this one. This isn't hard, but it's obnoxious, right? Just to write down to show, especially, I guess, the transitivity. Yeah. But that's important because what we're looking at is we're looking at, equivalence classes. So, it's just like 1/2 and 2/4 and 3/6. These are, it's actually an equivalence class when you talk about fraction. Show that the set of equivalence classes, the equivalence class of R comma S, I will denote by R over S. That'll be the notation I use, just like it's a fraction. Forms a commutative ring with identity. So you pick up an identity here. And even in the case where the zero is in there, and notice I didn't say that the identity is not zero. So in the zero ring, you can assume that that has an identity. With addition and multiplication given by the following formula that you're probably familiar with. And in C, part C says, show that if R has an identity, then there's a one-to-one correspondence between prime ideals of R that exclude S, that miss this multiplicative set, and prime ideals of R localized to S. And see if you can figure out how that correspondence works. Number two, I'm gonna do something right after we're done talking about this that'll help you greatly with number two. I'm gonna do something a little bit harder. The last theorem that I gave you last time in class said that a ring is Noetherian if and only if every prime ideal is finitely generated, right? There's an analog for PID. A domain is a principal ideal domain if and only if every prime ideal is principal. So you don't have, again, you don't have to check all the ideals. You only need the primes to be principal, and then everything is forced to pick. So my setup for number three is, suppose you have a commutative ring with identity. We say that the chain of proper prime ideals, P0, strictly contained in P1, strictly contained yada yada, strictly contained into Pn, has length n. Notice that we start counting at zero. So if I just have P0, I just say, oh, that's zero tall. We define the Kroll dimension of R, sometimes written as dim R, to be the supremum over all lengths of change of prime ideals. So if you look at your ring, you look at all possible change, it's supremum, that's the Kroll dimension. So given that, so Kroll dimension is basically how high you can stack your prime ideals, loosely speaking. So for example, in the integers, this is very simple, right? You've got 0, and then you've got p, where p is a non-zero prime. So it's got all these towers, 0, 2, 0, 3, 0, 5. And so, yes.
So zero dimensional means that every prime is not.
Zero dimensional is synonymous with saying that all prime ideals are maximal. That is correct. So let R be an integral domain and T an overring of R. There's always a mistake in here, and I'll tell you what the mistake is here. An overring is a ring that's contained between R and its quotient field. Show that if R is a field or a finite ring, here I don't need R to be a domain, right? Because a finite integral domain is a field. Then R is zero dimensional. So what I want you to do is show that if you have any field, or more generally any finite ring, which may have zero divisors, despite what I said up there, I'm gonna fix that, then it is automatically zero dimensional.
Wait, so what's the mistake?
The mistake is I don't want my finite ring to necessarily be a domain, right? Because I said in the beginning that's a domain, yeah. And number B, show that R is a PID if and only so, you know, you grow up learning that PID implies UFD, right? Here's kind of something better. PIDs are precisely the small UFDs. That is, R is a PID if and only if R is a UFD and you can't stack the primes too high. It's either dimension 0, in which case it's a field, or it's dimension 1, in which case it looks sort of like the integers. You have the 0 ideal and then a non-zero maximum. Number C, show that if R is a UFD, then any localization of R is a UFD, as per problem 1. So if you have any ring of fractions of a UFD, it's still a UFD. By the way, a theorem that we did just a while ago might make this problem pretty easy. And number D, show that if R is a principal ideal domain, then any overring is a localization. Right, so if T is any ring that's contained between R and the quotient field, it's a localization. This is actually a pretty astounding fact because if I walk up to you on the street and give you an integral domain with a quotient, okay, and then overrings in general are not going to be localizations. Certainly, all localizations are overrings, but there often are many rings that are not. So that's kind of a cool result. Okay, any questions on that? Okay. So I'm going through, just to get the ball rolling, I'm going to prove the theorem that we left off with last time, which was this really groovy thing about Noetherian rings, that say, hey, we only have to think about the prime ideals. Theorem. Are Noetherian if and only if every prime of R is finitely generated. Okay, this is a really cool theorem. Here's the easy way, right? If R theorem in every ideal is finitely generated. So if every ideal is finitely generated, then every prime ideal is finitely generated, right? So that easy peasy lemon squeezy. The interesting part is, hey, we only have to check the primes. So let's go this way. Now suppose each prime ideal of R is finitely generated. And suppose so this is going to be the strategy of my proof. I'm going to assume that every prime ideal in R is finitely generated. But let's suppose that R is not Noetherian. What does this mean?
Well, still the set of ideals that are not, finitely generated is not empty, so we can partially override.
Okay. So there exists, an ideal I in R such that I is not finitely generated.
The maximal ideal that he's gonna say.
And that is, it's kind of a Zorn's thing going on, right? Okay, so you've got one ideal sitting there somewhere that's not finitely generated, and the strategy is I am going to try to find an ideal that is maximal with respect to this property. Right? So I claim there exists an ideal maximal with respect to this property. And property meaning not finitely generated. Right, and so the idea is I hope to find this ideal that's not finitely generated, that is maximal with respect to that property. What does that mean? That means that any ideal that properly contains this ideal must be finitely generated, right? And even though this doesn't really apply, some heuristic evidence is, of course, the ring itself is finitely generated, right? It's generated by one. And so if you have an ideal, a maximal ideal that's not finitely generated, anything containing that must be generated by one. But let's be careful and make sure that such a thing exists. Let's let gamma be the set of J and R proper ideals such that J contains I and J is not finitely generated. So we're looking at the collection of all ideals containing I that are not finitely generated, all proper ideals containing I that are not finitely generated. Notice this is not an empty set. And partially by just under standard set theoretic. Right? So I want to throw Zorn at this. I want to say, boy, I'd really like to have a maximal element. Consider a chain called chain C, which is a collection of, let's say, J alpha. So index set. So of course, these are all ideals containing I. None of these can be finitely generated, and if I have J alpha and J beta, one of them contains the other. All right. Now let's let take the union of all these elements of the chain, we know, because we beat this dead horse over and over again, we know that U is an ideal. Right? And I is contained in U because it's contained in every element of the union. And actually, it's not finitely generated, so it's gonna follow as proper, but it's certainly strictly contained in R because no J alpha contains, one. The big piece of this is, okay, why, I mean, you take this union and maybe it's finitely generated, right? That's the worry. So we need to show U is not finitely generated.
It's kind of the same game we played with Noetherian.
That's right. Let's suppose U is generated by X1, X2, XM. So say XI is in, J alpha I, right? And suppose, without loss of generality, have J alpha 1 is contained in J alpha 2, contained in J alpha. You gotta love a chain, right? Therefore, X1, X2, XM are all elements of J alpha M. So but of course, U is the union of all the J alphas, therefore J alpha M equals U is finitely generated, which is a contradiction. So U is in gamma and is upper bound. Right, so Zorn applies. Applies, and hence, what was this? I is contained in P, where P is maximal with respect to, not being adjusted. Okay, so here's where we are so far. We've discovered that we have some ideal P that is maximal with respect to not being finitely generated. So the next move for us is to establish that this P is prime, right? Like I said, this will probably be helpful. This kind of whole idea is probably be helpful for problem number 2 on the next homework set. Okay, let's suppose A, B are in R, A, B is in B, but A, B, not. And we're out of contradiction. Suppose we have the product of two things in R being in P, neither one of them in there. Okay.
No,
What's that?
I'm just thinking that if we, take the generated by P and A or B, it will be finally generated, right?
I'm sorry, I mean,
If we take the ideal generated by P and A or P and B, that ideal must be finally generated.
so P, is strictly contained in PA. Because there's an A here, but not here, therefore PA must be finitely generated, right? That's the magic of this. Now, those generators suck, so I'm gonna make some better generators, right? Just something a little streamlined. I claim. Does anybody know where I'm going with this? Does anybody know how I might better wanna write these generators?
P plus RIA, PI plus RIA.
I'm gonna do it this way. Yeah, that's essentially it. I claim P1, P2, PK, and A. I claim I can do it. This is more where, let me, the notation is suggested, let me make sure. Where PIs. I claim I can do it now. Right, but let me justify this instead of just saying, notice that each xi can be written as pi plus ri times a, just by definition, right? Because each xi lives in here. And by definition, as you pointed out, that means that, hey, if you live in here, you're a linear combination of something in P plus a multiple of A, right? And this is exactly where I'm getting these PIs. Right here. So let me first notice that, so, and the reason for this is, of course, if I've got these P's and I've got A, then I have every one of these generators. Right? Everybody okay? And notice, but since PI is in P, and then is contained in A. Because all the generators are P and A is for A. So okay, so this is a better set of generators because I know that the PIs are in P and the A is well, the A is convenient.
So why can we assume that PA is finitely generated?
Because it's bigger than P. It actually
Max,
strictly
right,
contains P.
okay.
Okay, now, anybody know what, so, okay, so now, after all this effort, I've got this slightly bigger ideal than P that's generated by this nice, real slick, sharp looking set of generators. But what else?
You can write a typical element of P as a linear combination of this guy. And then we will prove that RA is in P. I don't know what to do then.
Right, let me define another ideal. This is kind of a conductor trait. Okay, so what I want to do now is I'm going to collect everything in R that blasts A back into P. Now, let me point out that this contains P, because for sure, everything in P blasts A back into P, right? This is an ideal. but it contains something else.
B.
It contains B. Because AB is a B. Right? So this strictly contains B. Right, okay with me? So I could do the same thing here that I did before, but actually with these generators, I don't need to clean it up, I don't think. Now, my last is I'm gonna make the following claim. This is not what I meant to say, my bad. That's what, yeah, so I can't clean this up, because J might be bigger than PB. I want this to be J. My claim is that J times the ideal PA is equal to P. Now, let me prove this for you. Notice if X is in J and P plus RA is in B. I'm not even gonna use my fancy generator, right? I'm just like Ferris Bueller's dad, I just wanna put it in the garage and look at it. So suppose you have X's in J and P plus RA is in P comma A. Then if you look at this product, this is XP plus RAX. And of course, this is in P. And this thing is in P. Because X blasts A back into P. So this is in P. So what we've shown is that J times the ideal PA is contained in P. Now, for the other equation, P is contained in J PA. Well, let's let P be in P, arbitrary. As was pointed out earlier, I can write P as R1 P1, R2 P2, plus RK PK, plus RA. Where now I have pulled my generators out of the garage here. I agree with that. So notice that, let me kind of do a little side hustle here. Notice RA is in P. Therefore, what can we say about R?
Check.
R must be a J because it's something that blasts A into P. Right. So since R is in J, R1 prime Y1 plus R2 prime Y2 plus Rm prime Ym. So P is equal to R1 P1 plus RK PK plus R, which is this, R1 prime Y1 plus Rm prime Ym times A. Right? And so, let's see, actually, that's not what he's doing this. This is in,
Yeah, but
this is this, so let me, and I work through this and everything. I claim, that P, I don't make this claim at all, is generated by P1, PK, up to, Y1A, Y2A, up to Y, there we go. I claim that, that's what I should have done, should have forgot about the product. So let me kind of run you through this here, so so we don't lose the thread. So the claim is P generated by P1, P2, PK, Y1A, Y2A, Y. So it's not quite J times that. I don't know what I was thinking. Let me point out that this containment should be fairly clear. Because each of the P's is in P. And since the YI's are in J, each YI times A, each of these are in P as well. Everybody okay? So the only thing that we have left is to show the other containment, and that's what we were doing here. So we have P is R1 P1 RK PK plus RA, which equals R1 P1 plus RK PK plus whatever I got over here for R, this thing. Which is, of course, RKPK plus R1 prime, Y1A plus R2 prime, Y2A plus RM prime, YMA. And hence, we get this containment here. Any element of P is generated by these things. And that is our contradiction. This P, not generated. So this establishes theorem. So basically what this theorem shows, or this technique shows, is if you have any ideal that is not finitely generated, there must exist a prime ideal that is not finitely generated.
So from this, do we get that ascending chains of prime ideals stabilize is equivalent to Noetherian, or is that?
No,
No. You can't do
no,
that.
and in fact, there's a famous example by,
Right.
Nagata, I think.
Before you're.
Oh, I'm sorry.
Just so I write it down in my notes correctly.
Yeah.
This is, this J thing is some
Right.
sort of colon ideal? Is that
That's
correct?
exactly right.
What-
Right.
So it's,
It's the conductor of, so it's everything here, so it's everything that conducts A into P, so if you like that colon notation.
I don't know, is there another notation?
It's everything that knocks A, the principal ideal A into the ideal.
Also. Why were we, considering the chain? Or sorry, when we set up our gamma, why were we only considering finitely generated ideals over I?
I hope I didn't say finite generated, I said, I hope I said not.
Not, yeah, sorry, not finitely generated. Why were we doing it over I? So let's assume that we ever use that back to the was over I.
No, but that just adds a little pizzazz to it, because now you know, you've actually got a stronger result than what I said. So if you've got any ideal that's not finitely generated, it's contained in an ideal that's maximal with respect to that property.
Thank you. So if you have evaluation domain that is
Sorry, one quick question.
Sure.
So
two-dimensional.
where were we using this inclusion? Or like, where were we showing this inclusion? B is contained in JPA.
We did, so because I didn't want to do JPA, I wanted to show the statement here that in fact, let me put some box here. Using the notation that I had approved, P is generated, so, well, my claim is P is generated by P1, P2, PK, and then Y1A, Y2A, YNA. And once I established this, that's a contradiction because P was not finitely generated. Right?
Okay.
Okay. Any others? Okay, so, let's go through this problem. This is actually kind of so we know from our experience so far doing this, when we did the Zorn's limit and whatnot, we know that if you union a chain of ideals, you get an ideal, correct? We also know, I haven't given this result, but it's an easy exercise to show. If you have an intersection of any collection of ideals, it's an ideal, right? It doesn't have to be a chain anymore. But there's something nice from intersecting chains and union chains of primes. So here is the next result. Proposition 1413. Suppose P alpha, some index set is a chain of primes. Then the union and intersection is a prime. Okay, so both of these constructions give you a prime ideal. Now, here's so the chain part, you need for this thing to even be an ideal, right? But once it's an ideal, it's easy to show, once you've got that it's an ideal, it's easy to show this is prime. You don't need chain for this collection to be an ideal, but you do need a chain for it to be prime, right? In fact, if it's not a chain, it's usually not. I won't say never, but okay. We know that the union of Pi alpha is because the P alpha from the chain, that's necessary for this to be an ideal. Well, yeah, it's not completely necessary because the largest one can contain all of them, but we need this fact here for this to be an ideal. How about prime? Well, suppose A, B is in Q, where A and B are elements of said ring, then A, B is in a piece of beta for some beta in the index set. Therefore, without loss of generality, A is in P beta. Right, because one of those elements is probably therefore, A is in the union P alpha, which is So, that's easy, right? The intersection. There's nothing to remark on about the ideal, because intersections of any collection of ideals, but this one's, it's not hard, but it's a little bit more to it. Now, let, B equal the intersection. I claim that, B is the top ideal. And suppose X, Y, Z. Okay. One from yeah. Now our burden, of course, is to show that Y must be in B, right? So what does it mean for X to not be in B? There exists a beta in the index set such that X is not in beta. Right? Now, let me break this down into two cases. Let P alpha be any suppose first, case one, P alpha is contained in P beta. Notice in this case, X is not in P alpha because it's contained in P beta where it ain't. Therefore, Y is in P alpha as XY. So since XY is in the intersection, it has to be in every one of them. XY is in P alpha, but X is not there, so Y must be in there. Right? Case two, suppose P beta is contained in P alpha. Well, in this case, since X is not in P beta, Y must be in P beta, which is contained in P alpha. Right? Therefore, Y is in P beta for all beta. Therefore, well, let me say all. Y is in the intersection P alpha. So intersections and unions of chains of primes are still prime. Let me give you a theorem that's a spin-off of this. Actually, a couple things, a couple of spin-offs. Theorem. Let I be an ideal in R. And P a prime ideal containing I. Then P can be shrunk I'll make that more precise, to a prime ideal minimal among all prime ideals containing I. All primes containing I. That is to say, if you have an ideal and it's contained in a prime ideal P, then I can shrink this down to a smaller ideal in P that is minimal among the set of all prime ideals it contains. And this is precisely because the intersection of a family of, the intersection of a chain of primes is still prime.
Just good old fashioned sort.
Yeah, that's right. I mean, so,
But we take the other way as our.
well, I mean, if you really want to be careful and go through this, what you could do is you could look at all chains of primes that contain, let me rephrase, all chains of primes that, between I and P, right? And then find a maximal chain, right? And in fact, I'm not gonna leave that as a mystery, because I'm gonna do a proof in a moment where I'm gonna actually do it as Lorentz limit and get a maximal chain. So you get a maximal chain of that, right? And then take that maximal chain and look at its intersection, and that'll be one. You'll see something very similar here. This is often called the next neighbor. There on 1.4.15. This is kind of an interesting, so this actually brings up kind of an important question that could be involved. I believe some facets are still unknown as to what partially ordered sets can you have that describe the behavior of the prime ideals, right? So if I walk up to you on the street and give you some ring and you look at all its prime ideals in the ring, right? That forms a partially ordered set, right? So if I walk up to you on the street and give you a partially ordered set, under what circumstances can you find a ring that has prime ideals that behave like that? Here's one restriction right here. Let P inside Q be distinct primes. Let P inside Q be distinct primes. Then there exists distinct primes P1 inside Q1. Such that P1, P1, and Q, and there is no prime properly between P1 and Q. Let me be more precise on what no prime properly. P1 and Q. This is kind of the next neighbors thing. So here's one of my patented little cartoons about this. So the idea is you've got big primes and small prime perhaps. What you can do is find primes here. Say this is Q1. And P1. So you sort of grow this one out. You sort of grow P out here, Q1, and you sort of shrink Q1 down to here. Such that these two are what we call adjacent primes. Adjacent meaning there's no prime ideal probably. There may be other ideals between there, but there's no primes. And so any partially ordered set that describes the spectrum, the collection of collection of prime ideals must obey this property.
So is it like discrete? Is that what's happening?
Oh, no, no, it could be, because there may be just this whole spectrum of stuff in here, right? And actually, to be able to put these ideals down is something that is not practical to do, because this depends on one's limit. And the proof of this is very similar to the previous one. We will go over that Monday. Don't forget, no math club today, it's First Friday, so unless you really love parades, I suggest you get off campus by at least 4 o'clock, because otherwise you're gonna get stuck here. But if you like parades, then knock yourself out. Any questions? All right, well, I will see you all on Monday.